Hello, welcome. In this lesson, we are going to talk about the existence and uniqueness theorem for a first-order initial value problem. Recall that a first-order initial value problem consists of a first-order ordinary differential equation of the form y prime equals some function f of x and y. Here x is the independent variable and y is the dependent variable, subject to the condition that y at x sub 0 equals y sub 0. For example, y prime equals 2y subject to the condition y at 0 equals 3 is a first order initial value problem. In this week, we would learn how to solve equation 1. But for the moment, let's assume that we have the solution. Y of x equals 3 times e to the 2x. We can verify that this function satisfies the equation. And this function also satisfies the initial condition. Y at 0, if we substitute x value 0 to the left-hand side, we would obtain the 3 from the right-hand side too. And equation 2 describes the unique solution to the equation 1. So this particular initial value problem, subject to the condition, has a solution and the solution is unique. Let's look at another example. Consider the following initial value problem, where f of xy is x times square root of y and y at 0 equals 0. We can simply verify that these two functions satisfy the differential equation and also the initial condition. So this initial value problem has at least two solutions. The solutions are shown in the figure. Both the solutions are passing through the point 0, 0. Now, two important questions concerning initial value problems. Does every initial value problem have a solution? Geometrically asking, does the ODE have a solution that passes through the point x sub 0, y sub 0? If a solution exists, is the solution unique? Geometrically asking, if the solution exists, how many of them will pass through the point x sub 0, y sub 0? The answer to both the questions are formally established in the following theorem. Let R be a rectangle defined by these two conditions. X is larger than A and smaller than B, and Y is larger than C and smaller than D. So we have a rectangle here without boundaries, containing the point x sub 0, y sub 0, somewhere here in its interior. If f and f sub y be continuous on R, then in some interval I contained in the open interval a to b, there is a unique solution of the initial value problem. Here f sub y stands for the first partial derivative of f with respect to y only. Before we move to an example, let's note the following points. The conditions stated in the theorem are sufficient to guarantee the existence and uniqueness of the solution to the initial value problem in some interval I. But they are not necessary. That is, the conclusion remains true under slightly weaker hypotheses about the function f. In fact, the existence of a solution can be established on the basis of continuity of the function f alone. However, its uniqueness is not clear. Geometrically, the uniqueness part of the theorem implies that the solution curves do not intersect. So if the solution exists and it's unique, there is only one solution passing through each given point. Let's look at an example of the existence and uniqueness theorem. By this theorem, the following initial value problem has a unique solution on an interval I containing the point x sub 0 equals 1. Since both f and f sub y, as given by negative y squared and negative 2y respectively, are continuous on some rectangle R containing the point A with coordinates 1, 1/2. The direction field and the solution curve with the rectangle is shown in the figure. This is a representative rectangle. It can be even larger. Let's consider another example. This initial value problem has a unique solution by the existence and uniqueness theorem. Since both the function f and its first partial derivative with respect to y are continuous on the rectangle R defined by these two conditions containing the point 2, 4. By the existence and uniqueness theorem, the given initial value problem has a unique solution. Even though we did not develop any method to solve this initial value problem, but we do know that there exists a solution to the problem. The rectangle is shown in this figure, which is in fact the upper half of the xy plane without the x-axis. Let's consider another example. This initial value problem with the same ODE but a different initial condition. Since both f and f sub y are not continuous on any rectangle R containing the point 0, 0, the existence and uniqueness theorem doesn't apply here. However, since f is continuous on R, the given initial value problem has a solution. But its uniqueness is, however, not guaranteed. In fact, as we saw earlier, that these two functions both satisfy the initial value problem for all value of x from negative infinity to positive infinity. Here, this is the interval I.